Hey, Chem 30, welcome to topic 3 of Unit 4, Solubility Equilibrium. This is where we're going to move back into that calculation-heavy sort of topic that we saw in Unit 3, Equilibrium. So when we're talking about equilibrium reactions, we're going to be focusing on a solubility product constant, which is a value that will tell us how much can dissolve in water at 25 degrees Celsius. It's specified at 25 degrees Celsius because we know as temperature increases, the amount that can dissolve also increases. So when we tabulate this information for different compounds, we always have it at 25 degrees Celsius. Okay, so compounds with no KSP in our booklet, and we'll see this chart in just a second, are considered to be very soluble. So if you look in our booklet for sodium chloride, for example, it's not there because it's considered soluble. If listed, the lower the number, the smaller the KSP, the less soluble it is. So in your reference book, you're looking for this table here. At the top, it says solubility product constants for compounds at 25 degrees Celsius. The very first one, barium carbonate, 5.0 times 10 to the negative 9. So very small. If we look one down, barium chromate, a little bit less soluble at 2.1 times 10 to the negative 10, and so on and so forth. Okay. This is nice. This table has the name, the formula, and the KSP. So if you get stuck on trying to figure out a formula, it might be on there and you have a little bit of a chance of getting the question right. So we're going to figure out which is more soluble of the pair that's listed. So generally when we're looking at these, all we need to do is look at the magnitude. So chromate is negative 10, where lead to chloride here is negative 5. So this is much smaller in the same way that 1 is smaller than 10,000. Okay, it's actually about that much bigger or that much smaller. It's about 10,000 times less soluble. So which one is less soluble? PbCr, that's about R04. There we go. So barium sulfate or silver 2 sulfate. Again, I'm just going to write the magnitudes here. So barium sulfate is 1.1 times 10 to the negative 10, 1.1 times 10 to the negative 10. And silver sulfate is 1.5 times 10 to the negative 5, 1.5 times 10 to the negative 5. We got that same situation there. So again, barium sulfate, much less soluble, or much more insoluble. All right, cobalt 2 hydroxide, negative 15. Wowzer, that is small. And copper 2 carbonate, 2.3 times 10 to the negative 10. So COOH3. And then copper 2 hydroxide is 4.8 times 10 to the negative 20. And this one is not anywhere on here, NaCl, sodium chloride. Why? We should recognize that NaCl is soluble, according to rule number 1 on our solubility rules. So the answer here, keeping with the vein of the other 3, the first of the 2, right? So all the way down is the left-hand column. Just random luck there. Alrighty, so a solubility product, or the solubility product constant, is calculated using this dissociation equation, okay? You'll notice that this here, the solid is always written first, so as solids break down. Now, there's a couple things that we need to draw our attention to. The number of ions become the coefficient, right? So if we had A3B1, it breaks down into 3A plus and 1B3 minus, right? So that's really all we're doing. We're balancing the ions there. So the number of atoms in that compound become the coefficients, right? So B and A here. This is a solid, and these two are always aqueous, and we include the charges. When we write the KSP expression, right, KEQ, very similar, we're doing products over reactants. So notice that the 2 AQ substances are in our expression, but the solid isn't. So this is really just over 1. We ignore the over 1 part because it doesn't change it mathematically, right? So this is what we call a solubility product constant expression based on a dissociation equation. So this is the dissociation equation. This is the solubility product constant expression. This is a really important chart. I'm going to get you to circle slide 48. It shows us that KSP is related to the concentration of the ions, which is related to the molar solubility of the compound, which is related to the mass, or we can calculate the mass solubility of a compound. Remember at the beginning of the unit, I talked about how solubility could be measured in multiple ways. Well, the ways that we're going to be focusing on topic 3 is using a KSP to figure out molar concentration of ions, to figure out the molar solubility of a compound, and ultimately figuring out the mass solubility of a compound. And to move from one to the next, it tells us exactly how to do that. So we're going to use a solubility equilibrium. We're going to use the empirical formula and the formula weight, which you should be good with from Physical Science 20. Okay, we have our first example here. And before I start this one, I'm going to tell you to go and grab your calculator, your scientific calculator, because you're going to be pausing the video to try some of these calculations on your own to make sure that you know how to use that. Okay, so we are going to determine the solubility product constant for silver bromide if the molar solubility for this compound is 7.3 times 10 to the negative 7 molarity. So what we're given here is we're given the molar solubility of silver bromide. So we're going to figure out the concentration of those ions when it's reached equilibrium. And from there, we're going to be able to write a solubility expression and eventually solve the KSP. So this is the compound, right? So silver bromide, we should be able to write the formula AgBr, pretty straightforward. So basically what's happening here is we've got a beaker and some water in it, and we throw in a bunch of silver bromide, so much that we get a super saturated, right? A solution that has some solid on the bottom, and eventually it forms an equilibrium between the ions of Ag plus and Br minus, and those reconnect and then form the solid again and some more dissolve, and eventually this equilibrium is set up. And that's what we're going to be using to figure out the KSP. So how much is a measure of how much dissolves to form those ions. So again, we've got AgBr. We're going to start with that, and it's a solid, and it forms this equilibrium reaction between its ions and that solid, AgBr and Br minus. Now, when we write it like this, we can express the molar solubility as this value here. And this value, when one of these breaks down, it forms one silver and one bromide ion. So if I know this is 7.3 times 10 to the negative 7, this number here has to be 7.3 times 10 to the negative 7, and so does this one. Don't let the scientific notation confuse you. Basically, it's a 1-to-1-to-1 ratio. Imagine it like this. If I have one car, I can take apart the car, and I'm going to get one steering wheel and one car body, right? So the same idea is being applied here. So silver bromide, this compound breaks up into this ion here, one of that ion, and one of the bromine ion. Okay, so I've got that. And we should remember that the KSP expression is the concentration of the two ions multiplied. So Ag plus in this case, and just one of each. So it's not squared, it's not multiplied by anything. So all we're going to do is take 7.3 times 10 to the negative 7 and multiply it by 7.3 times 10 to the negative 7. At equilibrium, those are the concentration of those ions. So all I got to do is put this into my calculator. Now, when I'm doing a question like this, instead of writing 7.3 times 10 to the negative 7 twice in my calculator, all I'm going to go is left bracket 7.3 times 10 to the negative 7, right bracket, and square that term. I'm less likely to make a mistake by squaring something than I am by typing it in, especially if it's scientific notation twice. So this works out to being 5.329 times 10 to the negative 13, and we're only going to take the first two digits, so 5.3 times 10 to the negative 13. Now, if you recall from Physical Science 20 or Pre-Cal 20 in math, when we multiply bases and exponents, we're summing the exponents. So, for example, 2 times 10 to the negative 10 times 2 times 10 to the negative 5 is actually, we take the bases and multiply that, 4. So 2 times 2 is 4. And then we take the base or the exponents and add them. So this would be 4 times 10 to the negative 15. So when we multiply negative 7 and negative 7, we would expect negative 14. But remember, scientific notation says there can only be one number in front of the decimal. So let's take a look at this one. Let's say we've got 5 times 10 to the negative 10 times 5 times 10 to the negative 5. What we're going to do here is 5 times 5 is 25 times 10 to the negative 15. But because we can only have one number in front of the decimal, and the decimal is really sitting right there in 25, right, behind the two numbers, we'd write this as 2.5 times 10 to the negative 14. And that's what we've got going on here. When we take 7.3 multiplied by 7.3, we're actually getting 53 times 10 to the negative 14, but we rewrite that as 5.3 times 10 to the negative 13. Okay, if all of that went over your head, here's the trick. When we're multiplying, we expect our answer to be within one magnitude, either bigger or smaller than the sum of those exponents. In this case, the sum of these exponents would be negative 14. We get negative 13. That's close enough. We expect that to be the correct answer. Okay, hopefully you've done this with your calculator and you've got the same answer as well. Let's take a crack at this one, a little bit more challenging. We are going to determine the solubility product constant of manganese 2 phosphate if the solubility is measured to be 9.8 times 10 to the negative 7 molarity. So what I like to do with these ones is to make sure that I'm doing the right thing is just write what the symbol would be. So the solubility product constant, anytime I see constant in there, that's KSP, right? There's where the S comes from, there's the P. So the KSP, we're going to work to determine the KSP if we're given a molar solubility. Molar solubility is always measured in molarity, right? So it's very easily connected. So the most common mistake is people are doing the reverse procedure because they're not looking at the question close enough. So when we're doing this, manganese 2 is Mn2 plus, phosphate is PO4 minus. So the formula for this one would be Mn3 bracket PO4 2 solid decomposes into 3 Mn2 pluses and 2 PO4 3 minuses. Okay, so you can see how this one's going to be a little bit more challenging. The solubility is still 9.8 times 10 to the negative 7, so we're going to put that value in there. But now for each one of these manganese molecules or compounds, I'm going to get 3 of these. So the concentration would be 3 times greater. So if the concentration of that molecule, Mn3PO4 is 9.8 times 10 to the negative 7, the concentration of the manganese ion is going to be 3 times 9.8 times 10 to the negative 7. And this one would be 2 times 9.8 times 10 to the negative 7. So what I'm going to do is I'm going to take these two values and write what this would be mathematically, just below it. So grab your calculator and do the same thing with me. So 3 times 9.8 times 10 to the negative 7, which works out to being 2.94. And I'm going to keep some extra digits here. 2.94 times 10 to the negative 6. And this is going to be, I'm going to divide this by 3 and actually then multiply it by 2. So dividing it by 3 just gets me back to that 9.87. And this works out to being 1.96 times 10 to the negative 6. All right, so we're going to write that KSP expression. So KSP is equal to concentration of Mn2 plus to the power of 3 and concentration of PO4 3 minus to the power of 2. Yes, I know we multiplied by 3 here and multiplied by 2 here. But the KSP expression and the reason why we do these two things are two different processes in chemistry. The 3 at the front and the 2 at the front are related to stoichiometry and chemical kinetics. But the 2 to the power of 3 and the power of 2 in the KSP expression, that's related to equilibrium. So we need to account for both when we're doing our calculation. So we multiply it by 3, then cube it, we multiply it by 2 and square. So this works out to being 2.94 times 10 to the negative 6 cubed and 1.96 times 10 to the negative 6 squared. Now, when we have some number, let's say we've got 2 to the power of 3 to the power of 2, this works out to being 2 to the power of 3 twice, right? So this would be 2 to the power of 6. So when we've got exponents across a bracket, we're multiplying. So we've got negative 6 times 3 would be negative 18 multiplied by negative 12. We're expecting something around negative 30. So let's put this into our calculators. So I'm going to go left bracket, 2.94 times 10 to the negative 8 to the power of 3. Hopefully you know where your power buttons are. Make sure that you're not working in that above line. If you have a calculator with 2 lines of display, make sure you drop back down to that main level. 1.96 times 10 to the negative 6 squared works out to being 9.76, and we can round this up to 9.8 times 10 to the negative 29. All your answers for KSP calculations will just be to 2 decimal places, or sorry, 2 numbers, 1 decimal place. So 9.8 times 10 to the negative 29. And again, that's exactly where I expected it to be. I mean, the answer's on the bottom of the slide, but I knew the magnitude should be around minus 30. Okay, welcome back. In this example, you can see that we are now moving backwards from hopefully a KSP into the molar solubility of silver bromide. Now, it gives us 0 information here. So we are having to move from something into the molar solubility. So if we can figure out the KSP, we can figure out the concentration of those ions and eventually the molar solubility. We're not given the KSP of it, but luckily enough, it is in your reference book on the page that looks like this. Okay, so we're just going to find silver bromide in here, which AgBr, and its KSP, it's alphabetized. Silver bromide is 5.0 times 10 to the negative 13. So 5.0 times 10 to the negative 13. All the questions like this, you'll either have the KSP from your reference book or it'll be given to you in the question. So what we're going to do here is we're going to write out what the dissociation equation would look like. So silver bromide breaks down into silver and bromide ions, and we don't know the molar solubility. So we're going to consider that to be X. Well, if X dissolved, it would form X Ag plus and X Br minus, right? If this was 3, this would be 3, and this would be 3. If this was 1.0 times 10 to the negative 10, this would be 1.0 times 10 to the negative 10, and so on and so forth, right? So we can see that procedure is going to carry all the way through. So well, let's write a KSP expression. Now, KSP is equal to the concentration of Ag plus and Br minus. And we know the KSP is equal to 5.0 times 10 to the negative 13. And we know the concentration of Ag plus, right here, is X. So this is going to be X multiplied by X. So we just get 5.0 times 10 to the negative 13 is equal to X times X, which is X squared. So if we wanted to solve for X, we would just square root this. And we get X is equal to 7.1 times 10 to the negative 7. And we're done there, okay? So the question asks to determine the solubility. The solubility is the X represented right here, okay? But we want to make sure that we communicate that and write our answer in a way that we know. So we're going to enclose the compound that we're talking about in square brackets. So we're going to say the concentration of that dissolves, its molar solubility, is equal to X. But we can't just say that. So we're going to say 7.1 times 10 to the negative 7. And then we need to include a unit for this, right? So molar solubility is measured in moles per liter, or we could write this as 7.1 times 10 to the negative 7, big M. They mean the same thing. Both are equally correct. So when we're doing this, we got to be careful that we communicate the molar solubility in moles per liter. Now, I do want to draw your attention to this here. You notice that 13, when we square root, it becomes 7. Same idea. It's just a reverse principle. We'd expect it to be 6.5, but we can't. It's really just a scientific notation. But I'll give you a little hint here. When we square root x to the 10, it becomes x to the 5. So this becomes x to the 5. When we cube root x to the 30, it becomes x to the 10. And when we fifth root x to the 50, it becomes x to the 5, right? So we can see that whatever number that we're rooting by, whether it's 2, 3, or 5, or 20, or whatever it might be, we're essentially going to be dividing the exponent by that. So it's a nice little check for us to make sure that we've done this calculation correctly. Okay, we've got another slightly more complicated one, but nothing too difficult. we're going to determine the concentration of fluoride ions in a saturated solution of magnesium fluoride. Same idea here, where we've got our beaker and we dump in some magnesium fluoride, which is MgF2 solid. It pools on the bottom, and then some of that dissolves into ions. So there's F minus, F minus. We want to figure out the concentration of how many ions are in solution. So if we can figure out the molar solubility, we'll be able to figure out how many ions are in solution. So let's write out this expression. MgF2 solid decomposes into Mg2 plus aqueous and 2F minus aqueous. And you can see how important it is to be able to name ionic compounds. If you're unable to do that or write the formula of them, you can't even really start the question, right? So you've got a real tough sled if you haven't got that basic skill down yet. So we don't know the molar solubility, so we're going to represent that by X. The concentration at equilibrium of the magnesium ion is going to be X, and the concentration of the fluoride ion is going to be 2X. Right? For every magnesium fluoride that breaks down, it produces 2 fluoride ions. So KSP in this situation is equal to concentration of magnesium 2 plus F minus squared. So we get X times 2X squared. Now, I don't know why. I say this every year and people still make the same mistake over and over and over again. 2X squared, I need to write this a bit more carefully. 2X squared is equal to 2X times 2X. There are 2 parts to this. There's the constant, and then there's the variable. Multiply your constants. 2 times 2 is 4. X times X is squared. Okay, so 2X squared is 4X squared. If we had 2X cubed, this means 2X times 2X times 2X. This becomes 2 times 2, which is 4, times 2 is 8. And then X times X times X is X cubed. Okay, so be careful with this. The number of times I see this becomes 6X3, or for some reason even 6X2, or I don't really know other combinations. Okay, this is wrong. Just be careful with when you're squaring things. We'll see more. There's lots of complex examples in your practice questions, so make sure you're doing all of those. So this becomes 2X squared times X, which is going to become 4X cubed. Now, I'm going to write this and include the KSP, which is given to me. So this becomes 5.6 times 10 to the negative 11 is equal to 2X squared is 4X squared, multiplied by X becomes 4X cubed. Order of operations really matters here. So I'm going to write this out very clearly over here. I divide by 4 first. Divide by 4 first. So I can punch this into my calculator. 5.6 times 10 to the negative 11 divided by 4 is 1.4 times 10 to the negative 11. 1.4 times 10 to the negative 11 is equal to X to the 3. There are 2 ways that you can put this into your calculator depending on how good your calculator is. There's going to be, most of them will have a button that looks like this. You're going to use that X, so you're going to put 3, second function, square root generally, that symbol in. So that'll give you a cube root. Okay, so you're going to cube root this answer. So if you're following along with me, I'm going to go second function this, 3. My calculator has an answer button, which I just plug that in and it puts it automatically in. All of your calculators should have that as well. If you use it, it's going to give you a little bit of security and save you a bit of time as well. But this works out to being 2.41 times 10 to the negative 4. So 2.41 times 10 to the negative 4 is equal to X. And you'll notice that that answer is not the same there. Hopefully you can see why. The concentration asks, the question asks, what is the concentration of the fluoride ions? The concentration at equilibrium of the fluoride ions is symbolized by 2X. So the concentration of the fluoride ions is equal to 2X, which is equal to 2 times 2.41 times 10 to the negative 4, which is equal to 4.8 times 10 to the negative 4. Concentration measured in, you betcha, molarity. Okay? Hopefully that makes sense. If not, I would pause the video, go back, try it on your own and see where you get stumped. And that'll give you a little bit more of an insight on which questions to be asking me if you need to come to the help session. Okay, welcome back to the last example here. What mass of chromium 3 hydroxide is able to dissolve in 500 milliliters of water if the KSP of chromium 3 hydroxide is 1.6 times 10 to the negative 30? Okay, right small. This is a pretty big example. So we're going to start out the same way that we normally would. If I go all the way back to this slide here, we can see that we have been given a KSP. We're going to figure out the concentration of those ions, figure out the molar solubility, and then eventually figure out the mass solubility using the formula weight. Okay, so there's quite a few steps in here, but then we're going to also deal with that 1 liter because it's asking us for how much can dissolve in less than a liter. Okay, so we're going to use a little bit of dimensional analysis at the end to help us out with this. So let's start by writing the dissociation equation that's going to happen. So we've got Cr bracket OH 3 solid decomposes into chromium 3 plus and 3 hydroxide ions, and these are both aqueous. All right, so if this is X, this would be X, and this would be 3X. So KSP is equal to the concentration of chromium 3 plus multiplied by the concentration of OH minus cubed. So 1.6 times 10 to the negative 30 is equal to X times 3X cubed. So 3x cubed is not 9, just so we're aware. 3x times 3x times 3x. 3 times 3 is 9, times 3 is 27. X to the 3 multiplied by x gives us 27x to the 4. So 1.6 times 10 to the negative 30 is equal to 27x to the 4. So again, order of operations. So I'm going to take 1.6 times 10 to the negative 30, divide by 27, pardon. Then I'm going to take my answer to the 4th root. All right, so I'm going to root it by 4. So I'm going to divide by 27, and I'll color code this for you. Then we're going to go in red and 4th root both of these answers, which is going to give us x is equal to 1.56 times 10 to the negative 8. 1.56 times 10 to the negative 8. What this means, X represents, right? So 1.56 times 10 to the negative 8 moles per liter, and I'll even write this, moles of CrOH3 dissolve in 1 liter. But the question is asking us in mass, which is in grams. So I can convert moles to grams using the molar mass from the periodic table. So chromium 3 hydroxide is made up of 1 times chromium, 3 times oxygen, and 3 times hydrogen. So chromium has a molar mass, I don't know, 51.9961. So 51.9961. This is 16.00. This is 1.01. So 51. Is it 50? Yeah, 51.9961 plus bracket 3 times 16 bracket plus bracket 1.01 times 3 equals 103.0261. So 103.0261 grams per mole. Right? I got all those masses from the periodic table behind me. So I'm going to use that. Notice that mole's on the top. So 1 mole of Cr bracket OH3 has a mass of 103.0261 grams. Okay, so moles are going to cross off here. And now I've got 103.0261 grams per liter, right? So the only unit I have on the numerator, the top, is grams, and the only unit I have on the bottom is liters. But it's asking us for 500 milliliters, not a liter. So what we're going to do is we're going to take that 500 milliliters and convert that to liters, so 0.500, and we're going to multiply by 0.5. So 0.500 liters. And now what happens is the liters are crossed out. and the unit I'm left with is grams, and that is a unit of mass. Okay, so I'm going to take the top and multiply it all the way across and then divide by the bottom. In this case, it doesn't have any numbers on the bottom, so it works out easily for us. So we got our bracket 1.56 times 10 to the negative 8 multiplied by 103.0261 times 0.5, and then divided by 1 divided by 1. It's not going to make any difference. This works out to being 8.0 on my calculator because I kept a couple of extra sig figs. 8.05. The answer down there is 8.04. If you had either one, I would mark them both correct. So 8.05 grams. So this means that about 100 millionth of a gram of chromium hydroxide would dissolve in 500 milliliters of water, which is exactly what we'd expect, right? We know that this is an insoluble compound because it has a KSP. So anytime we see a KSP, we expect it to have a very, very, very small amount that can dissolve in water, and that is the case here. So 8.05 times 10 to the negative 7 grams will dissolve in 500 milliliters of water. Okay, that is the last example. As always, reach out if you need any help. Otherwise, have a great night, Chem 30.